I think it's the first time I talk for 10 hours. My plan is to cover first of all, my plan is to try to be very basic and instead of introducing very abstract notions, I'll try to stick to very, I'll try to make things as directly computable as possible in what I'm doing. So in doing that, of course, I also have to skip some more abstract concepts, but hopefully you get more out of this approach. So my plan is today to talk about black holes in 4 dimensions. So this is all very well-known stuff from the literature, but I think it's always good to be reminded how this works. I'm planning to talk also tomorrow afternoon. I mean, I have 2 lectures on Wednesday, but I was planning to move the first one to tomorrow afternoon at 3 instead. So if there's no protest, at least. So today, we have 2 lectures. The one now, the one at 3, and then tomorrow. So today I'll cover 4-dimensional black holes, and let's see, maybe I can even start on something more, but I don't expect it. Then tomorrow, so this is at 3, I will start on more than 4 dimensions. I will introduce that a bit, and then I will talk about black brains or P-brains, and things related to that. And then probably Wednesday, I believe this is then at 11:30. I will start on something called black holes, which is a relatively new technique of how to understand high-dimensional black holes. And this is also what I will continue with on Thursday. I forgot when it is. It's in the. But if it's okay with you, I move the first 2 hours of Wednesday till Tuesday, so we don't have 4 hours in a row. Okay. So let me start on the 4 dimensions. So today we stick to 4 dimensions, and the subjects of today, what I will try to go through is the physical properties of black holes, or some of them at least. Then something called black hole mechanics, thermodynamics, and Hawking radiation, black hole uniqueness, and finally, I think maybe uniqueness is actually before, but anyway, we'll see. And then finally, the information paradox. In brief, at least, because that alone you could of course talk 10 hours about. So. Okay, so let me start very basic. What is a black hole? Well, a black hole is a solution of the Einstein equations. So you have, as you should all know, the Einstein equations. And over here, you have some space-time geometry dependent part. And here we have something that depends on what matter we put in our theory. And of course, as you all know, matter curves the space-time as a consequence of these equations. Yeah, for example, light rays bend, and so on. Due to if you have a curved gravitational field. So what happens if you have matter which is so condensed that I mean, you can condense matter so much that light cannot escape, because the matter curves the space-time, and then the light rays get bent so much that they cannot escape anymore. And then somehow you have matter that is really so heavy and dense that the space-time around it collapses. And that's when you have a black hole. So you can define an event horizon so I'll often just write EH for event horizon. So you can define an event horizon simply as saying classically that it's an area from which light cannot escape. If we now assume that T mu nu, so the energy momentum tensor of matter, is 0 outside the event horizon, so there's no matter outside the event horizon. That means that if we want to find a solution of Einstein equations outside the event horizon, then all we need to solve is this equation, that the Ricci tensor has to be equal to 0. And in this situation, so we are sort of imagining that we have the whole universe here, and then we have some event horizon somewhere in the universe. But outside that, you have no matter, and you should just solve this equation here. So in that situation, there's only 2 known solutions of the there's only 2 known solutions to this equation. So the first one is the Schwarzschild metric. Which looks like this. And this has an event horizon at the so-called Schwarzschild radius, which I call R0 in this case. Then we also have another known solution, which is the Kerr metric. I don't know if I can have it here, but I'll try. So this is slightly more complicated. And possibly it's not readable what I write, then just ask me what I'm writing. Okay, and then we have these functions. And for this function, this is a quadratic equation in R, so it has two roots, which we call R plus and R minus, defined so that R plus is the biggest of the two roots, like this. I'll write down an expression, but it cannot be here. Well, maybe I can write it here. So R plus minus is this. So, and this has event horizon as R equal R plus. Okay, so those are the two only known solutions, known metrics for this case, where you have no matter outside the event horizon. There's also some other conditions, but I'll come back to that. So, but let's take a closer look at this metric and first understand some of the properties. So, okay. So first, I'll talk about the mass and angular momentum. So if we think in terms of Newtonian matter or special relativistic matter, then we can define, we can easily define what mass is, right? It's just the integral over space and then the mass density, and we can also write this in terms of the energy momentum tensor over there, like this, right? The 0, component of the energy momentum tensor. So this is for ordinary matter. Everything is easy. We can define what the mass is. But for these two metrics, say for the Schwarzschild metric, for example, this is pure geometry, so we don't really have any matter to integrate over. So what do we really mean by a mass of a black hole? How do we define what a mass is? So basically, we define it in analogy with ordinary matter by saying that the mass of a black hole is such that it exerts the same influence, the same gravitational pull as an ordinary matter with the same mass. So we say same gravitational pull as a Newtonian special relativistic point mass m means that the black hole has mass m. So instead of computing this, what we do is to try to figure out what is the gravitational pull the black hole exerts on its surroundings, and then define the mass of the black hole indirectly from that. And this means that instead of looking at this highly complicated geometric object, or complicated or not, I mean, then what we need to do is actually just to look at first ordinary Newtonian or special relativistic matter, and then understand how to define this gravitational pull for that. And then afterwards we can compare with the gravitational pull of the black hole. So what we do is we consider a Newtonian localized matter distribution so some matter here with some energy momentum sensor, and then there's an observer which has some distance which we call r, and which is very large. And then we want to find out how this person is influenced by the matter. So to do that, what we do is we look at Einstein's equations in the approximation, where the metric is almost the Minkowski metric. So I'm sure this technique should be familiar to you from general relativity courses. So we take a small perturbation of the Minkowski metric here. Right? Maybe I should write this. This is the Minkowski metric. Just this. Then there's some steps involved that actually I'll come back to later, but for now I'll just skip them and tell you what the result is. Because then, so what you have here, you have a energy momentum tensor which is localized, and we say that it's not so big that, I mean, it only exerts a minor influence on the gravitational field, so we only have to compute a linear correction to the Minkowski metric from the Einstein equations, and then we put in all this in the Einstein equations, and then we solve them, and then we find out what this perturbation of the metric has to be to correspond to this energy momentum tensor. Okay, and I'll come back to that later because we need to generalize it a little bit in higher dimensions. But for now, I just want to mention that that if you look at large R, so far away from the matter, then the 0, 0 or TT component, whatever you want to call it, is to leading order -1 from the Minkowski part, right? And then a correction of order 1 over R, and then higher orders. So this leading correction here is, one can find simply the mass as computed from this matter distribution. So here I've just, I've looked at Newtonian matter, solved Einstein equations, and then I find that this is the metric far away from this localized matter. And then I can do that also so this was for the 0, 0 component. Then this is actually the only, you can sort of make a multipole expansion, and this is the only monopole term. Then there's higher poles. For example, there's a dipole term which gives you the angular momentum of this. So what is that? That is this term here. So this is the 0 phi term, where phi is the rotation angle of the plane that you are rotating in. So it's this angle here. And then you get an expression like this. And here J is then the angular momentum in that measure in that plane, and you can then write it down in a similar way as over there, like the following. So this is the angular momentum. So in this way, we see we can understand mass and angular momentum far away from this localized Newtonian matter, and then this tells us how that exerts a gravitational pull, because that's basically given by this leading order correction to the Minkowski metric. So we then just define mass and angular momentum in analogy with this, and say that, for example, in order for the black hole to have mass m, this should be 2gm for the black hole, right? So if we want to read off the mass of the Schwarzschild metric, we just make the same expansion for large r. So the Schwarzschild metric is this, of course. And then we compare this with that, and then we see the Schwarzschild black hole must have mass R0 over 2g, right? In suitable units, at least. I think I put velocity of light to 1. And similarly, you can go to the Kerr black hole, where you have both the mass and the angular momentum. So this was for the Schwarzschild. Then for Kerr, you have to read off both this and that one. And you read off that for the Kerr black hole, the mass is again R0 over 2g, and J is a R0 over 2g in terms of the parameters for the Kerr metric. so any questions to this part? This was probably very basic, I hope. So it's clear to you how we measure mass and angular momentum of black holes, right? More or less at least. Okay, so now we will go over to something slightly more advanced. I will briefly tell you what a killing vector field is, because the next thing I want to introduce or talk about are the symmetries of black holes. So in order to talk about the symmetries, I have to introduce what a killing vector field of a black hole is. And I'll often write KVF for killing vector field for the abbreviation. So killing vector fields is important if you want to understand symmetries in general, but specifically also for, well, it's important for understanding symmetries of metrics or symmetries of spacetimes. And actually it can also be used to make a different definition of what it means, of what an event horizon is. I will briefly come back to that, I think. So we consider here a four-dimensional manifold or space-time. And we will choose some local coordinates in some coordinate patch of the space-time or the manifold, which I call x mu. And then we'll talk about, as we will look at a vector field. Yeah, so I call the manifold or the space-time, I call it M. So we look at a vector field on this manifold for space-time. And then what does it mean to have a vector field? Well, it means that for each point P in M, well, for each point P in M we have a vector, and this vector we can write using this local coordinate system like this. And at that point, this belongs to the tangent space of the manifold at this point. So this is the tangent space. Tangent space of M at P. Okay. So then I would like to tell you what does it mean, a flow of a vector field. So a flow of a vector field, what it means is that we basically integrate the vector field because it's a smooth map. So a flow, say of the vector field V, is a smooth map. That maps the manifold to itself, it also has an index T, which belongs to the real numbers. So for each T, it maps the manifold to itself in such a way that the derivative of this map is equal to the vector field at the point, at the transported point. Okay, so you can sort of make a picture that of this flow. So say we have t equals 0, and we have some vector here. And then for t equal 1, this map maybe displaces this, or could displace this line to another line here for t equal 1, and then this vector would the derivative going through here of the flow would be tangent to this vector, and you will get this vector when you differentiate at t equal 1, right, here, and so on. This t equal 2, you get this vector, and in that way, just by differentiating this map, you get a vector field everywhere on your manifold.
So what's t on the left side? On the right side you fix.
Sorry, what?
So in this picture you fix your point and then start. On the left side we have the t in the definition.
Ah, you're here. Yeah. So this is for a certain. Here t is also fixed. So this is it's the this function differentiated with respect to t for t equal t. I mean, we can call it t prime. I mean, like I don't know. You could say like this, I mean, if you want. That answers your question, right? Yeah. So this differential, it can be t equals 0 or t equals 1 or t equals 2, etc. And in that way, you recreate the whole vector field by differentiating this map. So that's called the flow, and it has some properties. So first of all, the flow, well, there's some further conditions. So first of all, the flow at t equals 0 should be the identity map of the manifold. And you also want that the flow, if you add two numbers here, you want that this corresponds to what do you call it? The combination of the two functions. So you first act with sigma s, and then make that map, and then on that you map with sigma t. Okay, so it's like, suppose this is 1 plus 1, right? Then you can get to 2 by first going here and then here in some sense, right? So that's what this ensures. Then you can, I mean, I'm just going to be very brief here because I don't want this to turn into a differential geometry course. And I just want you to have some rough understanding of what a Killing vector field, I mean, or maybe you already heard a lot about it, I don't know. Then you can write this down in local coordinates, this map. So this I'll just tell you how this works. Then this map basically in these local coordinates can be written like this. So the reason, of course, there's an index here is because when we want to point to a point on the manifold with the local coordinates, we have an index, right? Because we have 4 dimensions. So that's why there's an index here. Anyway, so if t is equal to 0, then it's just the identity map. So we just map the point to itself. So then it's just the same coordinates as we started with. But if t is not equal to 0, but very small, then this changes a bit, and then we simply get a vector field, because that is precisely the first derivative, right? So by this definition, you should get that. And then there's of course higher order terms as well. So then okay, this all seems very simple, but then the question is now how do we drag things along the flow? And there's something called Lie dragging, which is a way that you mathematically can make sense of dragging something along a flow. So, like if you have a vector here, you would like to know, you would like to be able to transport it here, and then know exactly what it is. So you sort of want to be able to take not a vector field, but just a single vector at that point and be able to drag it over here. And that is called Lie dragging. And before considering vectors, we consider functions. So for functions, let's say we have a function that goes from the manifold to the real numbers. And then we want to define the function, a new function which we drag along this flow. So that new function is simply f of the flow. I mean, it's very basic. So you simply combine the two functions, and then you have dragged the function along the flow, right? And then it depends on what this t is, how far you dragged it. So if your t is equal to 1, you only drag the function from here to here in the manifold. Okay. And now, since we understand this dragging for functions, we also want to understand this gives rise to a derivative, namely the Lie derivative. Because we can basically compare the value of the function, since the function is defined everywhere in the manifold, we can compare what is the value, say if we drag it a little bit over here. So what is the value of the function if we drag the value over here, or if we just read off what is the function, or what is the value of the function here, And this gives rise to the definition of a Lie derivative of a function. So basically, we just compare the dragged value to the actual value and then differentiate. Well, and then take the limit, I should say. And if you compute this in local coordinates, then this derivative becomes equal to this v mu, and then the derivative of x mu, or of f with respect to the local coordinates. So it's basically a derivative where we can it's basically a way to define the derivative of a function in the direction of a vector field, right? And this should be pretty clear from the explicit version, right? So this is all very, I mean, we didn't need all this mathematics to understand that. That is pretty basic, but then when you go to other things than functions, for example, vector fields, then you need to understand things a little better. But actually first let me say one more thing about functions, namely, suppose we have that this thing was 0, right? Everywhere. So what would that mean? That would mean that when we drag this function, then it doesn't change, right? Because this measures the change in the function when it's dragged, right? So this being 0 means that the function doesn't change by being dragged. And this means that you can say this function have a symmetry with respect to this vector field along the vector field. Because it doesn't change when we drag the function. The function doesn't change when you drag the function along the vector field. Okay. So we can also consider now dragging a vector field. So suppose we drag a vector field. Let's call it W. And we want to drag that along V, the other vector field. So then I will just postulate that the Lie derivative in this case in local coordinates becomes equal to the following. And this you can also write as the commutator of V and W. So that's just the definition of this. So you see here that if you compare this expression to the function, to the expression for the function in local coordinates, there's an extra term, right? I mean, this last term is an extra term as compared to a function. So why is that extra term? Well, that's basically because when we try to drag a vector along the flow, we cannot really compare the value of the vector here and here, because the tangent space that we have here and here are two different tangent spaces. So this term basically mathematically takes that into account. I will not explain how, but you should just believe me in that. But one thing you can see, one way to see that this term has to be there, that it all makes sense, is to try to think what happens if we drag the vector field along itself. Well, then nothing should happen, because the vector field is not changing along its own flow, right? So if we drag the vector field along itself, it should give 0. And you can see that this is precisely such that this extra term precisely makes sure that dragging the vector field along itself is 0. Right? So that's a way to see that it makes sense. Then we would like to use this for metrics. So in general, one can define these Lie derivatives for any tensor. And since the metric is just a specific tensor, we can also define it for the metric. So the result of that is the following. So if we have a given metric G mu nu, the Lie derivative is just this. So the first term here is the same as before, the functional part, so to speak. And then we have two other terms which takes into account that this is a specific tensor. So actually there's an easy way to, from what we know, we can actually derive these two extra terms, because what we can do is, the Lie derivative is supposed to be a derivative, hence the name, right? But that means that in particular we allow to use the chain rule, because that should work for any derivative.
So what's the difference between second and third?
That I exchanged the mu and mu indices. Maybe it's not readable, but I don't know. But here mu is here, and here mu is there, right? And here there's mu and mu. I don't know.
Okay, no, it's...
Okay. But good you ask. Okay, so what we can do is, to understand these two extra terms, we could just define a scalar. Like this. Namely, we take another vector field. It's not important what it is, just some other arbitrary smooth vector field. And then we can use this to define a scalar, right? And then we know how a scalar transform. That is just what we learned over there. And then we can use the chain rule for this scalar. So this is, one expression for the derivative, but we can find another one using the chain rule. Namely, we can find the derivative of all this. So first of all, it's the derivative of the metric saturated with this vector field, and then we take the Lie derivative of vector field 1, the first vector field, and then we take the lee derivative for the second vector field. This is just a elementary use of the chain rule, right? And then you see that we know what this is, because that's what I wrote here, right? This is what we would like to know. I mean, this is what we would like to derive. This one, you can just use this expression over here, and the same for that one. So in that way, you can actually derive what this is using the chain rule. So it's like once you have it for the scalars and the vector fields, you can derive everything else using the chain rule. All other possible tensors. Okay. So I hope you have some understanding now of what it means a lee derivative of a metric, because now we will try to apply that. Because what we're interested in now is, say we have a given vector field and we have a given metric. What does it mean then if the vector field and the metric is such that the lee derivative is zero everywhere? This basically means, just like in analogy with the function, that when we drag the metric along the flow of the vector field, the vector field, so the metric doesn't change when we do this. And this means that we have some symmetry along the flow of the vector field, right? So we can say that G mu nu, the metric, is invariant to dragging it along the V, right? The vector field V, which is just another way to say that the metric has a symmetry. So you define a killing vector field. So say you have a given metric, then a killing vector field for that metric is so a killing vector field V for that metric is simply a killing vector field such that the lee derivative is zero. Okay? So if you want to look for symmetries of metrics, you have to look for these killing vector fields. So for example, we can go and look at these metrics here, and then we can list all the vector fields that you have, and you want to list them, you know, all the linearly independent, of course. So for example, if we take the Schwarzschild metric, maybe I can put it over here. So for the Schwarzschild metric, what are the vector fields that we have? Sorry, the killing vector fields that we have. That is just that, first of all, this one because there's a symmetry to dragging along the time directions, or symmetry to time translations, you can say. And then you have some other ones. Slightly more complicated. You have three other killing vector fields.
The first one, this is DR or F?
Sorry, yeah, it's good you asked because I'm not very.
No, this first I mean X. It's D.
This is DDT.
And it's X. What's X next to phi?
This X.
Yeah, but D phi, yes.
DD phi, yeah, sorry, yeah. Yeah, okay.
But there's no anything along R.
Yes, so there's nothing along R because the metric is not invariant going along R, right? I mean, so there's no symmetry because the metric actually changes if you increase or decrease R. Yeah. Whereas if you would increase or decrease phi, nothing changes in the metric.
Some combination because the along theta also changed that we have.
Yes. So that's why there's two terms here, you can say. But let me explain that because that's a good point. So as I said, this is the symmetry of time translation, and these symmetries here are related to the spherical symmetry of the metric. So if you, I mean, what you can do is simply take the definition, this one, right, and try to apply it and see that it really is a killing vector field. For this one is pretty clear, right? I mean, yeah. So you know that. I mean, you know that this two-sphere is embedded in R3, right? So that's you know, if you want to choose a rotation angle for S2, there's three ways of doing it. I mean, there's infinitely many, but if given x, y, z here, you know, you can either choose x, y, x, z, or y, z, right? So there's three possible definitions of your rotation angles, and that sort of explains these three linearly independent killing vector fields. So if you would choose slightly different coordinates from another point of view, you could write this in terms of p of some rotation angle, and then the two others would look complicated, and so on. So it's just because we chose a particular coordinate system that this one looks complicated. Sorry, this one looks simple and the two other complicated. Anyway, then you can check that the commutators are like this. So these commutators are the ones, the definition of this commutator is the one I wrote before. In the commutator of two vector fields. This is actually the commutator relations for SO3, which is the symmetry group for the two-sphere. And then one can also check, starting from this equation, that there's no other possible linearly independent killing vector field of the Schwarzschild metric other than these four. So that you can also find out. So if you have some free time, you can try to do it. Any questions to this? So let me mention the ones for the Kerr metric, and then maybe we have a break. So for the Kerr metric, we just have two linearly independent killing vector fields, namely time translation and the rotations. So you can see that going from the Schwarzschild to the Kerr metric, we have broken some of the symmetry of Schwarzschild, right? But as you probably already know, if you take the special case of Kerr where A is equal to 0, you get back Schwarzschild. So for the particular case of A equals 0, the Kerr metric becomes Schwarzschild, and then you again have these symmetries. But anyway, for A different from 0, you only have these two killing vector fields. So you have broken this spherical symmetry, and you only have rotation symmetry. Okay. So I don't know how long breaks. Yeah. Sorry.
It's the y and z. It's the x, y, z linearly independent.
Yeah. These are all linearly independent. Yes.
So it looks like if you times y by cosine phi and z by sine phi, you can annihilate dB theta. I mean, linear combination of y and z. You can't back.
So you mean if you multiply this with cosine phi and this with sine phi?
Yeah, and minus.
And minus. Yeah, but no, that's true. But I mean, the point is that I mean they're only linearly independent in the sense, but that's a good thing to find out. So if you say you have two killing vector fields, right? Let's call them x and y. It doesn't have to be these ones. And then you want to create another killing vector field, right? Then you can of course add them or subtract them, etc. But what you want to do is to say you have one function here, and then another function here, let's say, right? So you of course allowed that in the sense that this gives you a new vector field, but it's no longer a killing vector field. So if you have so a killing vector, the space of killing vector field is a linear space, and you can only act with constants. Like you can only, if you have two vectors, you can only. You can add objects, or you can multiply with a constant, but you cannot multiply with a function. Then you break the killing vector field. Then it's just a vector field. So that's okay. So let's take how long break? 10 minutes?
10 to 15.
10. Well, let's say 10 minutes. Yeah. Okay, thanks. I think the break is up, so what I would now want to do is to use this for something. Namely, I want to define the concept of stationary and static spacetimes. The definition of a stationary, stationary, asymptotically flat space-time is such that first of all, there should exist a coordinate that we here call R, such that for R going to infinity, the metric asymptotes to the Minkowski metric. More generally, to the Minkowski spacetime. But with the metric including the R coordinate like this. So this is the asymptotically flat part. And then the second part is that there should exist a killing vector field T such that for R going to infinity, we have at least approximately T equal d dt of this metric from Minkowski space. So where d dt is the time translation and the generator of time translation of Minkowski space. So this is what we mean with a stationary asymptotically flat spacetime. And we can always find coordinates I mean, here, I only sort of define this T or R being large, right? But it's always possible to find some particular set of coordinates for a space-time such that outside a possible event horizon in some coordinates we call T, R, phi, theta. We have that the time translation that the killing vector field that we have can be written like this, where this T is the T of this coordinate system. So we can always change our coordinates of our metric so that this is true everywhere, at least outside an event horizon. So this is what stationary asymptotically flat spacetime are. Then we also have to define what a static asymptotically flat spacetime is, and that is basically just so static asymptotically flat spacetime. That is basically just where you have an extra symmetry, namely that in this coordinate system here that you specifically chose for this purpose, you have the extra symmetry that T can go to minus T without changing the metric. So it basically means that it should be such that it doesn't really matter whether you evolve time forwards or backwards. Then we can look at the metrics that we now have. Because so this symmetry means in particular, you can see that all the components which only include one time direction of the metric, like GTR or GT theta or GT phi, has to be equal to 0 because they get a minus under this transformation. Right? So static spacetime has to have these components equal to 0. So we see that the curve metric is not a static asymptotically flat metric, but instead the Schwarzschild metric is, because here we can take T to minus T without changing the metric. So what we find is that the Schwarzschild metric is static and asymptotically flat. So the asymptotically flatness I didn't really make the case for, but this is just taking R going to infinity and see that you get this metric here, right? So that should be obvious. So the Schwarzschild metric is static and asymptotically flat, whereas the Kerr metric is stationary and asymptotically flat. So are there any questions to this? Yeah.
Why that components must be 0? Can it be like you have dt and you have some R function in front?
Because that could absorb a minus sign.
Yeah, let's say GT phi, right? If you make this transformation, like if you say make the coordinate transformation T prime equal to minus T, right? Then under this coordinate transformation, just using the usual transformation of the metric on the coordinate transformation, you just get that this is equal to T prime phi is equal to GT phi. So you can view this as a coordinate transformation, right? And then you see that there's this minus, and then it has to be 0 if there should be an invariance. Right? So more questions to this? So it's clear to you then what a stationary and a static asymptotically flat metric means, right? So and we've now categorized the Schwarzschild and the Kerr metric according to this. So now I will turn to uniqueness of black holes. So the Schwarzschild and Kerr metric have the following properties. So first, they are both stationary asymptotically flat spacetimes. So notice here that I also call the Schwarzschild metric a stationary spacetime. So that's just, I mean, it is a stationary spacetime. It's just, it has even more symmetry, which also makes it a static spacetime. So, okay, so it has the feature that it is, that they both have the features that they are stationary asymptotically flat spacetimes. Then they have an event horizon somewhere. So they exist an event horizon. And outside the event horizons, the metrics that we have obey our solutions of the pure gravity Einstein equations. So the Einstein equations without matter, which is just this, right? So these are three properties that I defined more or less what means for you, right? The question is now, so question. The question is now, are there other metrics with same properties? But not equal to any of these two metrics. And the answer is that there aren't. So there are no other metrics that obey these, that have these three properties. So the answer is no. And so in other words, if we combine these three properties, then by some not so easy mathematics, we can derive that the metric we started with, that, I mean, say we have a metric that obeys, that have these three properties, then the metric that we started with has to either be the Schwarzschild metric or the Kerr metric. There's no other metrics. This is formulated by a series of so-called uniqueness theorems for black holes. So they fall into various cases. So case one called Israel's theorem, and also Hawking had something to do with it. So the first case basically says that if we have property 1, 2, and 3, and also say in addition that the spacetime has to be static, then the metric of the spacetime is the Schwarzschild metric. And here one can notice in particular that this means that the space-time is spherically symmetric. And if you think about that a little bit, that is a pretty striking result. Because nowhere in these assumptions have I assumed anything about spherical symmetry, right? So I've only assumed that there's some sort of time translation invariance, and it's asymptotically flat space-time, there's an event horizon, and then it solves the Einstein equations without matter. So, you know, you could imagine, if you didn't know these theorems, that that there exists some, like if black holes should behave more like matter, you know, you could have a black hole which has a weird shape, right? And clearly such a black hole would not have spherical symmetry. So what this result, I mean, this is a very deep result. This tells you that the only possible event horizon we can have is one which is perfectly spherically symmetric. Okay, so then the second, yeah. So again, like if you compare to matter distributions, right? Then there could be infinitely many. There exist infinitely many static distributions. With all possible multiple moments. So the multiple moments is what, like, I mean, if the multiple moment higher than the monopole moment is non-zero, it means that you have something that deviates from spherical symmetry, right? So there's an infinite number of like if you are very far away from an object and want to understand the physics of it, you could measure all its multiple moments, right? And there's infinitely many of those. So what this is telling us is that basically you only have to measure the monopole moment, because you already know that the solution has to be spherically symmetric. And this metric is only defined, it only has one free parameter. So if you measure its mass of the metric, then it's completely defined, right? Whereas if you had a matter distribution, like the Earth or whatever, you cannot say anything like that, right? So black holes are very different from the ordinary matter in this sense. Then we have case 2. So this is Hawking, Carter, Robinson, and actually, I should say, to be completely fair to the mathematicians, in their opinion, this one is not really proving what I'm going to write. From the physicist's point of view, it is proven, but not from the mathematician's point of view, because they really want all the dots on their eyes. But anyway, the theorem here is, we assume now, again 1, 2, and 3. And then you assume that it's not static. So specifically that it's not static. And then you get that, I guess you guessed it already, that the metric is the Kerr metric. And as part of this, there's something called a rigidity theorem, which is what Hawking's part in this is, which is, over here, if we take case 1, you can loosely speaking say that that finding this killing vector field ddt, well, let's call it T, gave us 3 extra killing vector fields, right? Over here, there's something similar, namely that if you have the killing vector field of time translation, you find 1 extra killing vector field for the rotations, so dD5. And this is called the rigidity theorem. And this rigidity theorem basically just says that whenever you have a stationary asymptotically flat spacetime, you always have 1 rotational killing vector field. So this is what Hawking proved. That doesn't prove then that it's the Kerr metric. You have to do some more work to prove that. And that's actually where the Einstein equations come in, because the rigidity theorem doesn't have to necessarily, the rigidity theorem works more generally than for pure gravity, solutions of pure gravity. The rigidity theorem is much more general than that. But if we then say that we look at solutions of the Einstein equations, pure gravity, without matter, then Carter and Robinson have shown that it's really the Kerr metric which is the only possible measure. And this is also quite striking. It's like, in this case, in some sense, well, in this case, you have even less symmetry than over here. Because you specifically say that you cannot invert the time, right? So you have less symmetry in this case. But then you're still able to define what all the multiple moments of a black hole should be, and they are all unique, given just, I mean, you can see this is a two-parameter family of metrics, so it's completely unique if you given only the mass and angular momentum in this case, right? Or given only R0 and A. Then, as far as I understand, I'm not a mathematician, but as far as I understand, the mathematicians have some problem with the rigidity theorem. I mean, that's where they have some, I don't know what their problem is, that I wouldn't be able to tell you. But it's because, well, I mean, one reason, I don't know if this is their problem, but one extra assumption you have to make in the rigidity theorem is that you have to assume that the metric can be seen as that the components of the metric can be seen as analytic functions, so you can sort of extend everything to a complex space. This is a rather strong assumption, at least if you're a mathematician, where if you're a physicist, it's just something that brings you further. Yeah. So I think perhaps it can be that the problem they have is that they don't know how to prove this rigidity theorem without the analyticity. I think it's something like that. But, anyway, what's next? Yeah, so all this can be generalized. I mean, here I only took the case of neutral black holes, no matter. Then you can generalize it to, for example, to charged black holes with electric charges, magnetic charges, and so on. And that's also uniqueness theorem in those cases, and it's very similar. You have it. Okay, so to summarize, what did we learn now about black holes? So all I've talked about, I've restricted to general relativity, which is a classical theory. So the statements I've been saying are only about classical black holes, of course. So what do you know about classical black holes? Well, nothing escapes from behind the event horizon. Right. Sorry?
They haven't defined what's event horizon.
Well, that's true. So well, I said that it was event horizon is something where light cannot escape, from which light cannot escape. And you can mathematically make that a much more rigorous, write down mathematically what it means that light cannot escape. I mean, so mathematically it means that null geodesics are not able to leave from behind the event horizon. So you can take like Laurentian manifold, and then you can look at non-geodesics of the manifold, and then you can sort of see like that there are some surfaces for which in your space-time that non-geodesics can never pass through traveling speed. It has to be future directed non-geodesics. I mean, if they're past directed, it's another story. And then you can define sort of the, you know, then they can go closer and closer, and then you define the event horizon as sort of the limiting surface that. So there's some rigorous mathematical definition, which is basically just based on that light cannot escape from behind the event horizon, or that said more carefully maybe non-geodesics cannot come out of the event horizon. You can only go in to the event horizon. I mean, I could make a much more elaborate story about that, but yeah, that's a choice. Okay, so nothing can escape. The black hole can only absorb. Not emit. Right? And then we know that at equilibrium, a black hole is characterized by very few parameters. So mass, angular momentum, electric charge, magnetic charge. There can be some more parameters you have to define for more complicated theories. It's a finite and very short list in any case. So back in the 60s, they hadn't found completely all these uniqueness theorems, but they found the Israel theorem, and they had the suspicion that something similar was true for stationary space-time in general. So back in the 60s, they saw that this created a problem, because these two statements basically means that we lose information into the black hole. So for example, we can throw in a planet or just an astronaut or whatever. Well, oh, sorry, that was not my sorry. I wanted to say something different. Like, as you know, some type of stars can become black holes. So you can evolve a star into a black hole, right? Or you can have an existing black hole and then throw in some astronaut or something else. And then the astronaut falls into the black hole, and then you only have a black hole afterwards, right? So the point of this is that before, in the before situation, you have much more complicated situation with many more. You would take many more parameters to define precisely the configuration of a star or the configuration of an astronaut, then the number of parameters you have afterwards when the black hole is in equilibrium again, right? So in the after situation, you only have, say, you only have, say, these 4 parameters, right? But in the before situation, you have an enormous amount of information that you would need to characterize fully the state of the spacetime. So in this sense, we looped information into the black hole. And this means that, in particular, this means that entropy outside and event horizon can decrease by having the black hole absorb matter. So, a possible resolution of this that I'll come back to very soon is, of course, to say, well, maybe also the black hole has an entropy. Well, how can you make sense of this? Because the black hole has only very few parameters. So there's something very strange going on here. And the point of this is, and this is of course in part what we're still struggling with, but part of the resolution is to go to quantum mechanical black holes, as we shall see. But anyway, in the 60s, when they only knew the classical physics, this was quite a problem.
So, sorry, can I ask you a historical question? Because I really have no idea. What before, say, you could talk about the 60s.
Yeah.
So before the knowledge of the entropy of the black hole itself.
Yeah.
What did people actually believe about the entropy of a black hole before the area law, before all of this was explored?
Well, they didn't have any, they didn't know that there wasn't. They didn't suspect that there wasn't an entropy before Bekenstein came up with that idea.
So they thought it didn't have entropy.
Yeah. Okay. What they then were trying to resolve it, that I don't know. But it was posed as a problem that you, in this way, could lose information.
But it could be resolved by just saying that whatever the entropy of the black hole is, whatever the equation which describes it is, you know that it must. But the problem is that the problem is classically the black hole is only described by 4 parameters. So that gives you if you count the number of bits of information in this, the entropy is extremely small, right? So it's like what is it, log 4 or something. So there's almost no information related to a black hole in this sense. So the problem is that classically there's no way you can give a black hole a macroscopically large entropy from just these 4 parameters. Okay. So are there more questions to this part? Because otherwise I go on to the next part.
Or actually, maybe the time is up. I can see. Well, that's very nice. That's perfect. Okay, so just before we ask if there's additional questions. So the next thing I go over to is to define surface gravity and renderer space and area of event horizons and black hole mechanics and so on. So that I will start on at 3. And I should also say, sorry for only saying that now, I plan to, I have some lecture notes. They are handwritten, so don't have that readable, but I'll try to give you a link or something to them in case you find them useful. So if you didn't make notes or something, then
We can scan them and put them on the website of the school.
yeah, exactly. So we will figure it out. Okay, so are there any more questions just before we? Okay, so let's go to lunch then.